Hello, welcome to this new video. In this video, I will be talking about a specific example of how to use probabilities in a positive corona test. I just want to say this is not just a real scenario, this is just for the sake of understanding and fun. So the numbers we are going to see are not real numbers and the results, this is just for understanding. And we are going to be playing around with the Bayes Theorem. We are going to see how to use the Bayes Theorem for a specific example and have fun and learn during this interesting journey. So if I have the following question for you, let's suppose I got a positive corona test and the test has an accuracy of 96%. And now the question is, what is the probability I have actually corona given the test results? So this might seem very simple, which indeed is very simple exercise, because if we notice, we already have the solution. This problem is just giving, there is no much information, there is almost nothing, it's just, we just go make a test, we got positive corona, and what is the probability that we really have corona? Well, we just look what is the accuracy of the test. So therefore, we can say, we have a probability of having corona of 96%, which indeed is a very high probability, and therefore we can assume that we have corona. So probabilities in general are a very important, crucial tool when we want to take decisions, because if we have a number which is very close to 1, we can assume that, this is happening, this is very likely that this is happening, so let's take following strategies, assuming this reality. So, but let's think the following. Let's suppose that in this scenario, we have more information. Let's suppose that we are in a city that has a very low corona cases. Let's suppose we don't have symptoms. Of course, we know we don't have symptoms and have corona. But let's also suppose other data that, for example, we haven't had any contact with any person of corona. We have been some way isolated, we don't have many contacts recently or something like that, and we can think about it, we can say, we can model in some way and say, let's suppose we have a very low chance of having corona. Let's suppose this number is 2%. So in this second scenario, we have a probability of getting corona just of 2%. However, I go to make the test again, and I still get a positive corona test with a 96% of accuracy. So the question now is, do I have really corona? Or what is the probability I have actually corona given the same test results? Especially given also this new information of 2%. Is it going to be the same result of 96% or is it going to be something different? Well, and this is when the Bayes Theorem came to take place, and we are now going to model these examples to understand better how Bayes plays a role. Let's start to modeling this problem. So let's suppose we have the random variable x, and this random variable will have two values. Let's suppose 1, and we have x equal 0, only two values. So x equal 1 means that we have corona, and x equal 0 means that we don't have corona. So when we are trying to solving a probabilistic problem, it's very important to model and put a name to every variable we are facing, every variable we have into the model. So, and what about, we have other variable we are going to use to this in this model, which is called T, and T means the test result. So if we have T equal 1, means that the test was positive, and if we have T equal 0, means that the test was negative. Therefore, we want to see how we can model, or with all this information we have here, how we can model the probability we want to compute in our problem. So we have that we want to know what is the probability of x equal 1, which means that we have corona, but given the fact that the test was positive. Or in other words, what is the probability I have actually corona given that the test was positive? So if we look closer, this is a conditional probability, something you probably have seen in probability lectures, and we can formulate this number, this probability we want based in the Bayes theorem. So let's suppose we have probability of x equal 1 and t equal 1. This is gonna be equal to the probability of x equal 1 and t equal 1 over the probability of t equal 1. We can decompose this by, this is gonna be the probability of t equal 1 given x equal 1, and times the probability of x equal 1. All of this, was too long, and all of this over the probability of t equal 1. So every term here has a name, and we are going to see what is the name of every one here. So this probability we want to compute, incorrect color, sorry. This probability we want to compute is called posterior probability. And this probability here is the likelihood. And this probability I am highlighting here is what is called the prior probability. Or in other words, has another name, like is the belief. So we have here the Bayes theorem. All of this here, all this expression is the Bayes theorem. And we are going to play how we can compute, given the information we have in the problem, how we can compute the posterior probability, which is indeed what we are looking for, which depends of the likelihood and the belief, or the prior probability, which is what is the probability that we have corona, which is indeed the number we saw in the previous slide, which is 2%, which means what is that general probability that we have, that belief, that prior information in our model. So by writing down these values we have here, we know that the probability of t equal 1 given x equal 1, which is the likelihood, this is just asking, okay, what is the probability that I can test positive in corona given that I actually have corona? Which, in other words, this is the probability that is given in the exercise, which is the accuracy of the corona test, which in this example we are using 96%. So the other question would be, what is the probability of x equal 1? Which is the general question of what is the probability of having corona. So the probability of having corona is 2%. because it's the prior information we have, it's the belief we are using in our model. And finally, we have the probability of the testing being equal 1, or what is the probability you can have by going to make the test and having the test positive. So this is on the other way, this requires a little more, because we are going to decompose this probability, and because this information we don't have it directly, but we are going to decompose in the following slide. So we have previously that the probability of x equal 1 given t equal 1, which is what we are looking for, is gonna be equal to the probability of t equal 1 given x equal 1, which is the likelihood, given the probability of x equal 1, all of these over the probability of t equal 1. By applying some probabilities rules, like the marginalization, we can decompose this denominator in the following expression, which means this is going to be equal to the sum up of the probability of x given t, and we are going to sum up over all x values here. And we keep denominator the same expression. However, we can still decompose this denominator, because this value we have here, we don't have it, and this decomposition is going to be equal to the following expression. We just keep the numerator the same expression, but now we are going to decompose this joint probability into conditional probability times exactly as the denominator, but we are going to sum up all the values of x, which in other words we're going to have a final denominator equals to the following expression. Which is plus the probability of x equals 0 times the probability of t equal 1 and x equals 0. Which this means, we are just going to sum up all the values, all the different values of x. We're going to have here x1, x1, and we have on the other way x0 and x0. So this means that we are going to sum up all those values, which in this case is just only 2, because only we have the case of having corona or not having corona. And this is the great expression, the general expression for this particular example. So there are some questions you might have here, like for example, which are maybe you might ask, what are the value of this probability? Well, if we know that probability of x equal 1 is gonna be 2%, this value here is gonna be 0.98, and if we know that the probability, the accuracy of the test is 96%, which is the case of, okay, if we have what is the probability of having corona, given that we have the test positive. So in this case is the other way around. What is the probability of having the test positive given that I don't have corona? Maybe if we ask this question, which is let's try to highlight this here again. If we ask this question here, this probability, which is the question of, okay, what is the probability that the test is positive given that I don't have corona? we know that is a low probability, which is 1 minus 0.96 is going to be equal to 0.04 or 4%. And the same happened with this number, because this number here was obtained by 1 minus 0.02. So now we have all the numbers in this expression. We have every single value. So we make a substitution in every one of these terms and we compute this expression, and we are going to have the following result. We're going to have that the probability of having corona given that the test was positive is going to be equal to 0.32 approximately, which means, in other words, that we have a 32% of probability of having corona given that our probability of having corona is 2%, which in other words means that, okay, if we have a prior information, if we have a data before doing our test, and we know that we have indeed a very low probability, we are in a chance, we are more likely to be in a chance in the test were wrong, in the test that a test was not exactly accurate. So that's why it's impressive if we can notice that we have a bigger low, because we have from 96% the probability went down to a 32%, which is very surprising, because 32% is most close to zero, or in other words, is more likely to not have corona than in the contrary of having 96%, which means that yes, we have corona here, the most likely. So it's a way, it's an exercise to show how the probability changes given prior information, that we can change all the model given this belief, these 2%. And now we have a new question. We can think a little bit about this, because if we notice the prior information, which this 2% we use, change completely of a scenario in which we are very likely to have corona to a scenario of having very low chance of having corona. So I asking myself, and how much the prior information might affect this final result, of how much the prior information has the power of change a decision regarding having corona or not in this specifically example. Okay, let's see the following slide. How this there is an interesting graph that we can see in the following slide. We want to know how much the prior information affects the final results. We can figure out this by drawing the following curve we can see here in the slide. We have in the x-axis the probability of having corona, which is probability of x equal 1. And we have in the y-axis the probability of having corona given that the test was positive, which in other words is our posteriori probability we are looking for. So if we just get all the information from the previous slide and we make a drawing here, we will have the following curve, which is this curve here. And of course, I think it's important always to have the access limits, which is this is 1 here, this is 0, and we have here 1. So what this curve is telling us? So first, I think it's important here to notice that in our exercise we have that if we have a 0.02 probability, which is 2% of having corona, which is our belief, we will have as a result, let's suppose it's this point, we have 0.32, which was the last exercise we compute. So and we can appreciate that there is this kind of curve is telling us that if we move a little number, a little percentage here in our belief, we will have a high variations in our probabilities, in our posterior probability we are looking for. So it's interesting to notice, what will be the value? That's another good question. What will be the value of our prior belief in order to have 0.5 in our posterior probability? Because if we say, okay, if we have a prior belief that give us a number higher than 0.5, we can say that it's very likely that we have corona. So if we compute this, we will figure out that the number here is 0.04, which is telling us that for a little prior probability, for 4 percentage, 5, 6, 7, whatever, we can be in a range of numbers that will give us the higher chances of having corona, having a real corona after having a positive test. So in that way, it's interesting to notice that just a small number like 0.02% or 0.01, for example, can change the result of our probability, of our posterior probability. So as final question we can have here, it's what will be our prior probability if we want to have 0.96%, which in other words is the accuracy of the corona test, or is our likelihood. What will be the value of prior belief? So this corresponds to the first question we had in this video, in which the answer was exactly 96%, because our posterior probability coincides with the likelihood. Well, in this case, if we make all the calculus with all the equations we have in the last slide, we will have here 0.5. So what does this number is trying to telling us? It means that if we don't have prior belief, if we don't have prior probability, we are assuming that our prior probability is 0.5. Or in other words, when we take a probability results like 0.96% as a probability of having corona, that given we have a positive test, we are assuming that our prior belief is 0.5, which means that we don't have information. It means that we have a uniform distribution, and therefore when we have equal probability distribution, means that we don't have information. So therefore this is a very interesting way of approaching to Bayes theorem with this example, and trying to understand this type of curve, this type of results, and what it means to us. It's a key role, I would say, when it comes to understanding Bayes, and when it comes to understanding a lot of mathematical and computational stuff nowadays. I hope you have enjoyed this video, and if there was something that was not clear, please you can ask in the comments, or you can share with somebody, and it would be very nice to talk and to share about this video. Okay, thanks for watching, and bye bye.